An object from another star system just passed through our solar system, carrying a chemical record that may be billions of years older than the Sun. It was not going to stay. Its path through the solar system was one way, and astronomers had only months to read what was locked inside its ice before it disappeared back into interstellar space, never to return. 2 interstellar visitors had crossed our path before. Neither had given astronomers enough time or enough evidence to uncover the full story. The first appeared in 2017. Its name was Oumuamua, detected only after it had already made its closest approach, gone before anyone could study it properly. In 2019, 2I/Borisov arrived, the first interstellar comet with clearly visible cometary activity, its chemistry broadly similar to solar system comets. Both times the window was narrow. Both times the instruments available could only begin to characterize what the object contained. This time was different. The Atlas survey in Chile detected the object up on July 1st, 2025, moving at well over 130,000 miles per hour. Its extreme speed and hyperbolic trajectory confirmed that it came from interstellar space. Because 3I/Atlas was discovered so early, astronomers could mount the most ambitious observing campaign ever attempted for an interstellar visitor. Time to coordinate observatories across the world. Time to schedule the James Webb Space Telescope. Time to study an interstellar visitor before it disappeared forever. Could the chemistry locked inside a passing comet preserve a record older than our solar system itself? That's what Webb was about to find out. Ordinary comets circle the Sun. Some return every few years. Others take centuries. But they come back. 3I Atlas wasn't going to. It swept past the Sun once on an open path and kept going. There was no orbit to wait for, no second opportunity. Whatever answers were locked inside its ice, astronomers had only one chance to uncover them. Imagine reading what had been locked inside a comet for billions of years, without opening it, without touching it, simply by studying the light around it. Webb could do exactly that. As 3I Atlas approached the Sun, warmth reached ice that may have stayed frozen since before our solar system existed. That ice began converting directly into gas, sublimation, releasing molecules locked away since the comet first formed. They rose into an expanding cloud around the nucleus called the coma. Every molecule interacts with infrared light in its own distinctive way. Water leaves one signature. Carbon dioxide leaves another. Methane leaves another still. Webb's near-infrared spectrograph read those signatures in the coma's light, decoding what the comet was made of from hundreds of millions of miles away, without ever making contact. A real interstellar comet, behaving much like the comets astronomers already knew. At first, everything looked familiar, except the ratios did not add up. Webb detected water, carbon dioxide, carbon monoxide, and carbonyl sulfide, known as OCS, a sulfur-bearing gas that helps trace the cold environment a comet formed in, producing the most detailed chemical inventory ever obtained of an interstellar comet. The biggest surprise came from the carbon dioxide. Relative to water, carbon dioxide was roughly 7 to 8 times as abundant, one of the highest carbon dioxide to water ratios ever measured in any comet, whether from our solar system or beyond. It wasn't just unusually high. It was completely outside the range researchers were accustomed to seeing, suggesting this comet formed under dramatically different conditions than the comets we know today. Because carbon dioxide and carbon monoxide freeze at lower temperatures than water, their abundance relative to water can hint at the environment where a comet formed. The unusually high ratio could reflect an exceptionally cold birthplace or changes to the comet's outer layers during its long journey through interstellar space. Either way, the ratio alone could not reveal exactly where or when 3I Atlas formed. Its cometary nature was clear. Its birthplace was not. After 3I Atlas passed closest to the Sun, Webb looked again. This time, something new appeared: methane. From deeper layers, the Sun had only just begun to warm. It had been buried beneath the surface all along. That is why it only appeared in the later observation. Webb's mid-infrared instrument, MIRI, gave astronomers a different view at longer wavelengths. But by then, the comet itself had changed, and material from deeper layers was beginning to enter the coma. The amount of methane relative to water was surprisingly high, with few close analogues among solar system comets. Methane ice is far more volatile than water ice and survives largely in extremely cold environments, making it a useful tracer of very low formation temperatures. Buried deep rather than concentrated near the surface, its presence pointed toward an exceptionally cold region of the comet's parent system. Together, the evidence pointed to an unusually cold and chemically distinct birthplace. But knowing where it formed was only half the mystery. Working out when it formed proved far more difficult. Astronomers began by tracing its journey through the Milky Way, hoping its motion could reveal how old it was. Its speed was compatible with an origin in the Milky Way's older, thick disk, a population of older stars moving through a broader, more dynamically stirred region above and below the galaxy's flat plane. But the resulting age estimate, somewhere between 3 and 11 billion years, was still far too broad to settle whether 3I Atlas truly predated the Sun. The more decisive evidence came from somewhere else entirely: isotopes buried in the comet's water and carbon-bearing molecules. Webb's near-infrared spectrograph found that 3I/Atlas's water contains roughly 30 times more deuterium, heavy hydrogen, than water in solar system comets. That kind of enrichment points to water that formed in extreme cold. The comet's carbon told a different story. It carried unusually little carbon-13 relative to carbon-12. A pattern that points toward an older, more metal-poor galactic environment. Researchers compared that fingerprint against models of how the Milky Way's chemistry has changed over billions of years. The match pointed to a possible formation period 10 to 12 billion years ago, during what astronomers call cosmic noon, when star formation across the universe was at its peak. A separate study using the Very Large Telescope, examining isotope ratios in cyanide gas, found a similarly unusual pattern, further support for an ancient origin, even without independently pinning down the same exact age. Together, the evidence pointed strongly toward an ancient origin, but translating that fingerprint into an exact age was another matter. Think of the isotope signature like a fingerprint left billions of years ago. The fingerprint itself is real, but figuring out exactly when it was left requires a model, not a direct reading. The evidence strongly supports an ancient origin. The exact age remains model-dependent. Numbers that large are almost impossible to picture. If the 11 to 12 billion year interpretation is correct, 3I Atlas would predate the Sun by somewhere between 6.4 and 7.4 billion years, before the Sun ignited, before Earth formed. This frozen object may already have been part of a planetary system around an early metal-poor star. Not a planet, not a star. A frozen relic from an earlier chapter of the galaxy, passing through our neighborhood for the first and only time. Together, the molecules and isotopes inside 3I Atlas preserved more than a list of ingredients. They carried clues to the extreme cold in which the comet formed, the ancient environment it may have come from, and the billions of years it may have spent traveling between the stars. That preservation is what makes interstellar objects so scientifically valuable. A telescope pointed at a distant star can study its light, its chemistry, even the disk where its planets are forming. But an interstellar comet brings material from that system close enough for its molecules and isotopes to be examined in far greater detail. The raw materials it was built from, preserved since before it was ever flung into the dark. 3I Atlas is a time capsule, unlike those preserved in most known solar system comets, delivered here by chance and available for only a matter of months. Now it is fading back into the dark between the stars. But the search for the next visitor has already begun. Leading that effort is the Vera C. Rubin Observatory, now carrying out its 10-year survey of the sky. Its ability to detect faint moving objects means future interstellar visitors may be discovered earlier, giving Webb and other telescopes more time to study them before they are gone. With every new visitor, astronomers may begin building something they have never had before. A record of material from different star systems formed at different moments in the history of the galaxy. What the next interstellar visitor will carry and how old it will be remains completely unknown. But now we know what to look for, and we have the instruments to read it.